Section: Introduction. In this section, we delve into an insightful analysis of chart question answering, CQA, within the realm of visual language understanding, VLU. Our aim is to equip machines with the ability to understand and respond to questions based on data visualizations. While recent advancements in vision language models, VLMs, and multimodal large language models, MLLMs, have shown impressive performance in CQA, there are still uncertainties about their true capabilities. We explore the robustness and consistency of state-of-the-art CQA models, uncovering their limitations and guiding future research directions. We tackle key questions about the current state of CQA. Are existing models genuinely effective, or do their high average scores hide significant weaknesses? We investigate if models perform consistently across different types of questions. Simple questions involve extracting straightforward values, while complex questions require extracting multiple values, aggregating them, and making comparisons. Understanding how models handle these complexities gives us valuable insights into their capabilities. We also examine how models fare on specific aspects of chart understanding, such as question complexity and chart type. Models are tested on different types of charts and question types to gauge their performance and adaptability. We explore if the model's robustness, their ability to generalize across various variations, is adequately explored. The same dataset can be represented in multiple visual formats, each with unique characteristics. Exploring these variations can enhance the model's understanding of the data. To answer these questions, we evaluate leading CQA models on a carefully curated dataset that includes diverse chart types and question categories. We assess how well the models generalize across different visual representations of the same data and their robustness against variations. Our findings reveal performance gaps, especially with complex chart question combinations, emphasizing the need for improved robustness in CQA. Our contributions include a detailed analysis of current VLMs and MLLMs for chart understanding, introducing a new evaluation set with detailed splits across chart types and question complexities, and conducting a thorough robustness analysis to highlight the shortcomings of current models. Our research sheds light on the current state of CQA and provides valuable insights. The code and data are publicly available at the provided link. Moving on to the dataset preparation process, we selected the Chart QA dataset for our evaluation to analyze CQA model performance across various chart types and question complexities. The dataset covers diverse domains and includes questions generated by both humans and machines, offering a wide range of question styles. The presence of underlying tables in the dataset allowed us to create controlled visual perturbations for our study. Our experiments were carried out on the test set of Chart QA, comprising questions, charts, and corresponding tables. Section Summary. In this section, we analyze the performance of CQA models across various chart types and question complexities. We selected the Chart QA dataset for our evaluation, which includes questions from both human annotators and machine-generated sources, covering diverse domains. The dataset's underlying tables allowed us to create controlled visual perturbations for our study, conducted exclusively on the test set of Chart QA. Section: Chart and Question Labeling. In this section, we categorized both charts and questions based on their complexity levels to analyze model performance more effectively. The charts were divided into simple charts, which show a single entity over a data frame with 2 columns and no complex visual elements, and complex charts, which have more than 2 columns and involve multiple entities, making them visually complex. Similarly, the questions were classified into simple questions, focusing on data extraction with single-step reasoning, and complex questions, requiring multi-step reasoning, comparisons, and logical inferences. We introduced these categorizations while maintaining the existing division of question generation types, resulting in 8 categories. This detailed categorization helps us understand how chart and question complexity impact model performance, revealing their strengths and limitations. For our experiments, we selected various state-of-the-art models with different architectures, sizes, and training setups to evaluate their performance using a zero-shot chain of thought prompting approach. No additional reasoning aids were given to any of the models during evaluation. The models were divided into three categories: chart-based VLMs, generalist VLMs, and large MLLMs. Chart-based VLMs like Matcha, Unichart, and Diplot were specifically designed for chart reasoning tasks. Generalist VLMs such as QuenVL and CogAgent VQA focused on general visual comprehension tasks, while large MLLMs like Gemini 1.5 Flash and GPT-4o excelled in reasoning and visual understanding. To enhance the evaluation process, we introduced a new metric that includes additional checks for precise answer matching, such as alphanumeric string matching, strict year matching, and unordered exact list matching. This new metric provides a 5% leverage for numerical answer matching while ensuring accurate answers in various formats. Smaller VLMs like QuenVL, CogAgent, and InternLM face challenges in producing answers in the correct format. To address this issue, we implemented an LLM as an extractor approach using Gemini 1.5 Flash to extract answers accurately. Manual verification confirmed Gemini's effectiveness in preserving the original model's answers, demonstrating its role in improving the usability of smaller models without altering their intended outcomes. Section Summary. In this section, we categorized charts and questions based on complexity levels to create a modified evaluation dataset for our experiments. Charts were classified as simple or complex based on the number of columns and visual elements, while questions were categorized as simple or complex depending on the level of reasoning required. These categorizations allowed us to analyze the impact of chart and question complexity on model performance across various VLM categories, including chart-based VLMs, generalist VLMs, large MLLMs, and smaller VLMs. Section: Can VLMs reason consistently? In this section, we present our findings and analysis on how various models perform in answering chart questions. We looked at different types of charts and question complexities to see how well the models did. Our results are summarized in a table. While no single model excelled in all categories, GPT-4o and Gemini 1.5 Flash consistently showed impressive performance, with GPT-4o leading in most cases. Among open-source models, InternLM stood out as the top performer. Models like Matcha and Unichart, specifically trained on chart tasks, did well on augmented questions due to their training exposure. They performed best on simple questions but struggled with reasoning-based questions, indicating a need for improvement in their reasoning abilities. Across all models, we noticed a trend where performance was better on simple charts compared to complex charts, regardless of the question type. This difficulty in understanding and extracting values from complex charts is likely due to factors like overlapping data points and complex color resolution, making reasoning on such charts more challenging. For the same chart type, models consistently performed better on simple questions compared to complex questions. This difference in scores highlighted the limitations of certain models in detailed data extraction and reasoning. GPT-4o and Gemini 1.5 Flash showed strong data extraction and reasoning capabilities, with smaller models struggling more with questions requiring mathematical reasoning. When comparing performance on simple charts, complex questions, and complex charts, simple questions, we found that models like GPT-4 excelled in complex questions even with simple charts, while Gemini 1.5 Flash performed consistently across both categories. Models that are more generalist or chart-based tended to prefer complex charts over complex questions, indicating limitations in complex reasoning. We also identified common challenges for models, such as struggling with charts containing similar colors, tight pie charts, charts with summary statistics, and questions involving counting objects. Additionally, we conducted experiments to see how well models relied on visual information versus their internal knowledge base. Some models were able to answer questions correctly even with irrelevant images, suggesting a reliance on pre-existing knowledge. Our analysis showed that while models face challenges with certain types of questions and charts, there has been significant progress in chart question answering performance. Investigating the robustness and consistency of these models across different visual representations of the same data is crucial for understanding their performance in various scenarios. Section Summary. In this section, we analyze the performance of various chart question answering models across different chart types and question complexities. While no single model excels in all categories, GPT-4o and Gemini 1.5 Flash consistently demonstrate impressive performance, with GPT-4o leading in most cases. Models specifically trained on chart tasks excel on augmented questions but struggle with reasoning-based questions, emphasizing the need for enhancement in their reasoning abilities. Section. Our robust SICA dataset. In this section, we created the robust SICA dataset to test how well top-performing models handle different chart variations. We made 75 types of changes to simple and complex charts, such as adjusting colors, changing chart types, and modifying legends and axes. Each altered chart was carefully checked by experts to ensure it was clear and answerable. The final dataset grouped the changes into categories for easy comparison. We then tested various models using this dataset and found that most models struggled with the altered charts, with some performing better than others. Surprisingly, some changes actually improved model performance, like adding annotated data points and using specific chart features. This shows the importance of enhancing data extraction for better model performance in chart-based tasks. Section Summary. In this section, we created the robust SICA dataset by systematically manipulating various chart elements while keeping the underlying data intact. We identified 75 unique perturbation types for both simple and complex charts, covering color scheme changes, chart type variations, legend and axis modifications, among others. Through rigorous human verification and grouping perturbations into related categories, we evaluated leading chart question answering models using this dataset, revealing significant performance degradation for most models when faced with perturbations, with Gemini 1.5 Flash showing notable consistency and resilience. Section. Are there perturbations which are always detrimental to model performance? In this section, we delve into the analysis of perturbations that impact model performance when dealing with chart datasets. We found that models perform well on standard datasets but struggle with robustness when faced with visual perturbations. While annotations generally help, most other perturbations decrease model accuracy. Logarithmic scales pose a significant challenge due to the difficulty in data retrieval. Models also face difficulties with horizontal chart variations, especially horizontal stacked charts, but perform better with vertical stacked charts. However, models also struggle with normal stacked plots and area plots due to the complexity of accurate data extraction. Stair plots and changes in chart scale also contribute to performance decline. These findings underscore the need for more robust models that can interpret visual information beyond simple cues. Our analysis suggests that certain perturbations are more effective for specific question types. For example, line charts are great for revealing trends and correlations, while stacked bar charts are less suitable unless data aggregation is explicitly required. Bar charts are useful for comparing individual values within a group but not ideal for showcasing correlations across different entities. Selecting the right chart types is crucial for accurate and efficient question answering, especially in domain-specific applications. The impact of each perturbation on model performance varies significantly. While the question and chart type play a role, certain perturbations consistently affect models positively or negatively. Annotations and chart elements in random colors are among the top-performing perturbations. On the other hand, stacked chart elements and logarithmic scales hinder model performance. Understanding these effects can guide targeted model improvements to enhance overall performance. Chart comprehension and question answering are vital research areas, but existing datasets have limitations in terms of size, question templates, chart variations, and domain specificity. Our dataset, Robust SECA, systematically perturbs all elements within a chart for a detailed analysis of factors affecting model performance. We also conduct a fine-grained analysis based on question and chart complexity, providing valuable insights into model weaknesses. Various modeling approaches have been developed for chart comprehension, ranging from end-to-end reasoning models to models converting charts into tables for reasoning. Recent work has focused on developing accurate models for chart tasks, but there is limited understanding of their failure points. Our study focuses on a broad range of models for chart comprehension and provides detailed insights into question and chart types that lead to model failures, offering crucial information to enhance model performance. Section Summary. In this section, we analyze the impact of perturbations on model performance in chart comprehension and question answering tasks. We find that while models perform well on standard datasets, they struggle with robustness when faced with visual perturbations, especially logarithmic scales and horizontal stacked charts. Certain perturbations, such as annotations and random colors, consistently affect model performance, emphasizing the need for more robust models capable of interpreting visual information effectively. Section: Vision Language Model Robustness. In this section, we explore the robustness of vision language models. We have noticed that various models can be vulnerable to attacks and disturbances, which has raised concerns about their reliability. To address this, we have developed a benchmark to test the robustness of models for chart question answering. Our study involves analyzing the performance of different models when faced with perturbed charts, using questions that focus on both structural and visual aspects. Unlike previous work, we focus on general reasoning questions to examine how changes in visual representations of the same data impact the model's performance.